Very much, Pete. Good morning to everyone. Excuse me. My name is Jonathan Rathsam. I'm from NASA Langley Research Center in Hampton, Virginia. I'm the technical lead for survey design and analysis in NASA's low-boom flight demonstration mission. I'm excited to share this presentation with you today. Thank you so much to the organizing committee for this opportunity. This presentation draws from other overview presentations that have been given by my colleagues. In terms of an outline, noise control problems are often broken down into source, path, and receiver components. So the first part of this talk briefly considers the source and path components of supersonic flight and sonic booms. The second part takes a more in-depth look at the public reactions or the receiver. And the third portion describes NASA's low-boom flight demonstration. My family and I live in Virginia, and my parents live in Southern Oregon, which is 3,000 miles away. Flying from coast to coast means a long day of travel. The goal of commercial supersonic flight is to get travelers to their destinations more quickly, so grandparents can spend more time with grandkids. There is an emerging potential market for commercial supersonic aircraft, and it's evidenced by several commercial programs. Despite the lack of standards for supersonic overflight noise or landing and takeoff noise for supersonic aircraft. NASA's vision is a future where fast air travel is broadly available to the traveling public. Future supersonic aircraft will not only fly over land without creating an unacceptable situation, but they'll be efficient, affordable, and environmentally responsible, especially when compared with Concorde. The main barrier to this vision is the restriction on overland supersonic flight. National research agencies like NASA and policy agencies like the Federal Aviation Administration play a central role in developing the data needed for a regulation change that would enable this market. So to open the market for supersonic flight, new environmental standards are needed, and the en route noise standard is viewed as the biggest challenge. Not only does it require proof of new design approaches, aircraft design approaches, but it has to replace current prohibitions. There is no relevant data that exists today. The sounds from the community response tests that were conducted in the 1960s with supersonic overflights were too loud to be even remotely acceptable. Data from a large and diverse population is a requirement. And of course, any standard that's related to supersonic flight needs to have international support. So the low-boom flight demonstration mission was proposed to generate this data, specifically to support en route noise standards, not based on speed, but based on acceptable sound levels. Supersonic flight has been around for 70 years. In the late 1960s, supersonic commercial aircraft were proposed and several major community studies occurred. Supersonic aircraft were flown over communities and a social survey was conducted to learn how the community responded to the sonic booms. And the results of the test showed that conventional sonic booms created an unacceptable situation. In 1973, commercial supersonic flight over land was banned. From 1976 to 2003, Concorde flew passengers supersonically over water, but had to slow down when they reached the land. Presently, NASA's low-boom flight demonstration is building an experimental aircraft, the X-59, which will be used to collect data on public reactions to quiet supersonic flight. For some context here, the conventional sonic booms from Concorde and other aircraft that were used in these community tests in the 1960s, those were on the order of 105 decibels. Let me get a laser pointer here. Right in this range here, Concorde sonic boom. That's comparable to nearby thunder or a car door slam measured inside the car. And both of those sounds can be very startling if you're not expecting them. By contrast, X-59's sonic thump over here is designed to be 75 decibels, which is comparable to distant thunder or a car door slam from 20 feet away. So the first part of the presentation, as promised, is going to briefly describe a sonic boom and how it's quieted. A sonic boom is the sound of a shock wave or a pressure disturbance that's created when an object travels faster than the speed of sound. Sonic booms are caused by supersonic aircraft, but also meteors or spacecraft as they enter the Earth's atmosphere, falling rocket boosters, supersonic bullets, supersonic missiles, and even bullwhips. As you see on the left here, when an aircraft flies faster than the speed of sound, it creates this pressure disturbance and it emanates in all directions. The most important thing to remember is that the sonic boom moves with the aircraft, like the wake from a boat, for as long as the aircraft is traveling supersonically. The plot on the right here shows a pressure time history of this disturbance at various stages between the aircraft and the ground. A pressure time history is something that you would measure with a microphone. As it travels away from the aircraft, the waveform goes through a process called nonlinear steepening because the higher amplitude components travel faster than the lower amplitude components. And this steepening process is key to quieting a sonic boom. It was originally thought that all supersonic signatures were far-field N waves. That's like what you see here, and it's called an N because it looks like the letter N. The early efforts at sonic boom minimization concentrated on producing longer duration, lower amplitude N waves, so going from panel A to panel B here. By the way, panel A sounds like boom boom, and panel B sounds more like boom boom. Just an illustration. In 1965, McLean discovered that if an aircraft at altitude was long enough, the supersonic signature arriving to the ground could still be in the midfield, and it didn't have to be an N wave. And this led to the development of a family of optimum non-N wave solutions, all of which would be quieter than N waves. An idealized limit is a signature like a sine wave that's shown here in panel C. It eliminates much of the high frequency energy from the signal. The plots on the right here show the waveforms on the top and the frequency spectra on the bottom for an N wave in red and a shaped boom in blue. And if you look at the bottom plot here, you see how much sound energy is reduced when you go from that red N wave to the blue shaped boom. The second part of the presentation now is going to focus on the receiver and what the research shows about human response to sonic boom. In the 1960s, two major community overflight tests occurred in St. Louis and Oklahoma City. Each test lasted half a year. In St. Louis, there were 76 booms, and in Oklahoma City, there were upwards of 1,200. This figure shows the percent of participants that were annoyed by various types of interference. Ultimately, the results from these tests showed that conventional sonic booms would not be acceptable. With sonic booms that were on the order of 2 pounds per square foot, the sound levels were comparable, as we saw before, to nearby thunder or car door slams inside the car. Now, one really important result from this testing was that indoor annoyance was found to be the key driver of non-acceptability. So why does NASA think that the current designs are quiet enough? With indoor annoyance as the key concern, NASA has conducted laboratory tests, tests in small communities, and tests in larger communities. These were all tests of increasing complexity that showed that, in general, the threshold of acceptable noise levels had been reached. And that's what prepared NASA to take the next step with flight tests over very large communities. In the interest of time, I'm going to skip the lab test results and focus only on community test results, recent ones. So in parallel with the laboratory testing, NASA has been working to identify and minimize the risks that are associated with community testing. A community test exposes the entire community to sounds while only surveying a sample of residents on their perceptions of the sounds. In 2018, NASA conducted a large community test using an F-18 research aircraft performing a low-boom supersonic dive to simulate the sounds of quiet supersonic overflight. So in this diagram here, this is the Gulf of Mexico and Galveston Island, and the aircraft would start a dive right around here, go into a supersonic dive, and the result of that was a really loud sonic boom sound over the water, but a quieter thump sound over the land where the survey participants and residents were. In terms of community engagement, the communications had to be tailored to many different audiences, such as elected officials at the local, state, and federal level. That communication started many months prior to the actual tests. The residents, the general public who would be exposed to these sounds, had to be informed via newspapers and press conferences, and also via the local city hall. The mariners who were on the water in this region exposed to the louder sonic booms had to be alerted, and that was done via the Coast Guard. The survey participants, of course, had to be recruited and informed, and there was also a large effort for STEM engagement in the local schools to explain what NASA was doing in the community. In terms of flying a research aircraft, this F-18, outside of the test range, a special air traffic control assigned airspace had to be prearranged, and environmental review had to be conducted. In terms of ground measurements of these signatures, there were 25 ground recording units that were stationed across a 60 square mile survey area. They were linked via a cellular network and linked to a host station. The field crew deployed and calibrated and retrieved these units daily. In terms of a social survey, it was a web-based survey that had to be developed. It had to pass governmental survey review. It had to pass research ethics review, and the participants had to be recruited via postal mail and enrolled in the survey. One of the key lessons learned from this whole activity was the need to automate and streamline data analysis after the test, and that's in order to meet the very swift cadence that's going to be needed for X-59 community tests. But most importantly, this test showed that NASA could successfully engage with the community in order to conduct this response testing. So next we'll spend a few moments discussing what data is needed for aircraft noise standards development. For more than half a century, community noise survey data has been plotted the way it's shown here. You have a response metric like annoyance level, and that's plotted versus a dose metric like noise level. And this is known as a dose response or exposure response relationship. And it has its roots in other fields such as psychophysics, pharmacology, toxicology, epidemiology. For context, this plot on the right here comes from the seminal community noise paper on dose response. So in order to develop standards for supersonic flight over land, two dose response relationships are going to be developed. The first will be a curve for single flyover events, and that curve will directly inform standards for certifying aircraft. The second is a curve for cumulative sound levels from multiple flyover events, and the second curve will inform guidelines for limits on supersonic operations. The primary noise annoyance questions on the survey and the response scales have all been standardized, and they've even been translated to many languages to enable comparability among surveys internationally. The definition of the response metric as % highly annoyed was chosen to keep the regulatory focus on those who are most affected by the noise. Shown here is some sample single event dose response curves that resulted from previous NASA community tests. The first thing to note is the high degree of scatter in the data, which is typical of social survey data. The second thing is that in both tests, if you look at 75 dB here, that's the design point for X-59, that's associated with a very low % highly annoyed. As a matter of practicality, the sonic boom community tests, they've all been panel surveys in which a panel or a group of survey respondents responds multiple times. And the reason is that it just isn't practical to recruit a member of the public and then only request a single response, especially when these responses are needed promptly after a flight. One consequence of having panel samples is the need for statistical models that account for the correlation among multiple observations from the same participant. So now let's shift gears from talking about the past to talking about the future. We've set the stage to talk about NASA's plans for a series of community tests that involve the X-59 aircraft. With the knowledge that we could design a supersonic aircraft and also that we could conduct a relevant demonstration with a research aircraft, NASA set out on the low-boom flight demonstration mission. It's a systematic approach leading to testing of community response to the sounds of quiet supersonic overflight. Phase 1 up here is aircraft development. It's currently going on with Lockheed Martin in one of the satellite offices that you were talking about. This one's in Palmdale, California, with the design, fabrication, and ground test of X-59. When ready, we'll conduct a series of envelope expansion flights to prove that the airplane is ready and safe to fly in the national airspace system outside of the test ranges. After that, we'll continue with Phase 2, which is the acoustic validation, and that'll be back on the test ranges. And here we'll be proving that the acoustic signature of the airplane matches what we set out to design. We'll conduct detailed in-flight and ground measurements of the signature of the airplane in preparation for community testing, which is Phase 3 and the payoff of the mission. Phase 3 will be executed over 2 to 3 years, starting in 2024, and it'll consist of several tests over different communities in the U.S. and possibly abroad. Even though the demonstrator will be a relatively small aircraft, lab studies and design work make us confident that the demonstrator will match the acoustic characteristics that are responsible for annoyance from sonic boom sounds. In particular, as you see in the top right plot up here, the demonstrator matches the low frequency sound that causes vibration and rattle in this range here below 10 hertz. The bottom left here shows a plot of data from a laboratory study in our NASA Indoor Sonic Boom Simulator. And it shows that annoyance to the demonstrator is similar to larger aircraft in the range of sound levels that are going to be used in community testing. The X-59 is driven by the idea of meeting a minimum set of requirements to meet the mission. The acoustic signal has to replicate a future larger aircraft, like we just discussed. We have to be able to operate X-59 using normal flight maneuvers that would be expected for commercial supersonic aircraft. You can see on the slide some of the performance and geometry features. It's important to note that it's a new and unique airframe that was designed to accomplish the signature shaping, but it uses many components from existing aircraft to reduce costs. And it's a research aircraft, so the payload is just a single pilot plus the flight test instrumentation. Here are some images of the airplane in fabrication. Some of the systems are supplied by NASA, such as the external vision system, which enables forward vision without a forward-facing canopy window. And the airplane is powered by an existing fighter aircraft engine. Recently, the aircraft underwent some ground testing in Texas, and it is now back in California, and the target for the first flight is later this year. So our focus is conducting community overflight tests to create the dose-response relationship between the level of sound exposure and community annoyance. And in order to define an international standard, a large, diverse, and representative population has to be tested. The test has to be long enough to establish the effect of repeated exposures. And although we'd like to test in unlimited locations, we have to account for the fact that we do have an experimental aircraft with operational limitations, and that drives the selection of airfields for use. Part of the planning efforts involve engaging the local community to create a trusting environment for the test. We plan a variety of public and STEM engagement opportunities as part of the overall approach. And even though our testing is focused on the United States, we know that international acceptance of this effort is important. So we're seeking to engage the international and regulatory communities to ensure that the data is acceptable. Now, because DataWorks is about collecting and analyzing data, and we had a great panel discussion this morning about managing data within an organization, the next few slides are going to summarize some of the key challenges on this project, as well as some of the strategies so far to overcome those. So the goal is to collect nationally representative data. If this were a standard survey like a political poll, we might begin with a list of all U.S. households and select a random sample to recruit for the survey. That approach won't work here for several reasons. X-59 can only operate from certain airfields, and its range is limited. Also, survey participants need time to get used to the sound of X-59, supersonic overflights, and we're talking about weeks. To measure the noise exposure, about 100 ground recorders are needed to be placed across the survey area, and the survey area is large, 1,500 square miles. That's the size of the state of Rhode Island. Finally, the total number of flight hours on X-59 is limited. So in light of these constraints, the mission plan is for a maximum of 5 community tests in different locations around the country. Each test will last approximately 30 days. So what is NASA's strategy to collect nationally representative data from a maximum of 5 community test sites? The strategy is to achieve qualitative, not quantitative, national representativeness. This mirrors the dictionary definition of representative as like or typical of others of the same class. The test sites will be chosen based on characteristics of interest in a process known as purposive sampling. Together, the test sites must be diverse in terms of geography, race, ethnicity, urbanicity, age, and income. Because the sampling of the test sites is purposive rather than random, the representativeness is qualitative rather than quantitative. Within each test site, the households will be randomly sampled for recruitment into the survey. Because the sound level of the sonic thumps is quite low, very few survey responses from the risk reduction testing were actually highly annoyed. That means we're on the lower tail of this dose response curve, close to 0%. And while that may indicate a high degree of public acceptability, it can also lead to questions about the effectiveness of the survey instrument and the modeling techniques. So how do you effectively model this binary response data when the observations are concentrated in the lower tail of the distribution? Here are a couple of strategies. The first is on the modeling side, and the second is on the experimental design side. The response scale itself is ordinal, so other dichotomizations of this scale can be considered, such as percent moderately plus annoyed, or percent slightly plus annoyed. But some assumptions are required then in order to generalize those results back to percent highly annoyed, which is what the regulators are interested in. On the experimental design side, it may be possible to get more highly annoyed responses by generating higher sound levels. However, that approach has some risks in terms of potential misconceptions in the public about a quiet supersonic aircraft. The project also has non-technical challenges, including a long time span, many resources to manage, and very diverse stakeholders. Just within NASA, the project is being worked at multiple NASA centers. There are a number of contractor teams that are involved. One contractor team, for example, is building the ground recording system. And just as a side note, from the panel discussion this morning, you're talking about being responsible for your own data and creating the own instruments to measure your data. And so that made me think of this effort to, these are very purpose-built ground recording systems for the purpose of this testing. Another contractor team is responsible for supporting NASA to plan and execute the community tests. This community test contractor team involves 8 companies with diverse skill sets, such as conducting surveys, estimating noise exposure by combining measurements and predictions. In terms of regulatory bodies, not only is the Federal Aviation Administration a stakeholder, but also its international counterpart, the International Civil Aviation Organization, which is part of the United Nations. To execute the community response tests, coordination is required with all levels of government, federal, state, and local. And most importantly, the public is a stakeholder, because the public will not only participate in these tests, but they will also live beneath future supersonic flight paths and fly on future commercial supersonic flights. And so in terms of the strategy for dealing with that challenge, communication is key. I think that's a theme that we've heard from the previous talks as well. Active stakeholder engagement is also key, because with points of contact that are spread across so many different organizations, those points of contact change. And you don't want to find out right when you need to interact with an agency that all of a sudden your point of contact there is no longer there. So you have to be active in engaging and maintaining the relationships before you need them. So to summarize and wrap this up, technology and design improvements have led us to this point where we can envision a possible future for supersonic commercial aviation that's both quiet and sustainable. Quiet overland flight is vital for achieving airline operations and eventual broad market access for the traveling public. NASA's low-boom flight demonstration mission was created to provide the key data that's needed to define standards for acceptable, quiet, supersonic overland flight. The X-59 aircraft is a unique design. It was created specifically to meet the requirements to gather highly relevant acoustical survey data. The build of the aircraft is well underway. We're expecting the first flight later this year. And this mission will culminate in community testing to begin in 2024. The result will be dose response data from overflights of the U.S. and possibly international communities. So with that, thank you so much for your attention.
Hi, Steve Rabinowitz, IDA. I was wondering, for the community survey approach, how do you compensate for the alertment factor? Basically, you're telling people, I'm about to make annoying noises. Tell me how annoying it is. And is that going to skew your data?
It's a really good question. We want the participants to participate in the survey, but we don't want to tell them we're about to fly, so pay particular attention. So the compromise that we've come up with, which was tested in this 2018 data collection in Galveston, Texas, was to send a text message or an email reminding them right after the overflight has occurred. Did you hear a sound? Please respond to the survey. Because it's important that the survey is filled out whether the sound was heard or not. And so you can't rely on the sound, having heard the sound, to be the cue to start the survey.
And actually, one other, do you also have to account for other non-human things, wildlife impact? Is that a separate survey that you have to do for this kind of project?
That's part of the environmental review that's required, absolutely.
Dominic Calder with Lockheed Martin. I'm curious, with the data sets that you had, a lot of 1960s data, 1970s data, and then, of course, the 2018, if there were parallel data sets that may not have the same type of data, like sound source. It may not be the same sound source, but it produces the same effects. So house rattles, for example, artillery ranges have a lot of house rattling. Helicopter training facilities also produce a lot of house rattling, which seem to be the highest incident or highest probable annoyance cause. Curious if there were any desires to look into those data sets as possible, a way to augment what you have going on, because those are real effects that happen every decade, not just 1960s or 70s.
Yeah, that's a great question. I think the bottom line of my answer is we haven't found a really effective way to leverage those data sets to shed light on this. Even the 1960s data, those were sonic booms, but I was pointing in the early part of the talk to the waveform and the differences in the waveform, and none of us have heard what a shaped boom sounds like yet. We have to wait for the first flight of X-59 to know what it sounds like, but there are limits to how much we can generalize from the existing data, just because the waveforms are so different, which is, and there's another component to this, non-acoustic effects, and something that we probably won't be able to control for is the meaning behind sounds. That also makes a difference. And whether, we talk about the blast, the community around military facilities where blasting occurs, and the degree to which the residents feel like their voice is heard. If they complain because it's too noisy, that can also affect the reactions. And these are very difficult to keep track of these effects and control for them in this type of testing.
Great. Well, that brings us to the end of our session.